Okay, now we are heading into the last topic section. This is about output analysis. By now, we've learned everything you possibly could know about how to create an effective discrete event simulation model, create random variates that capture the various processes that you are interested in. And the thing to understand is that no model, and this includes all simulation models, both of the kind that we talk about here and every other one, no model is an end in itself. Every model is really a means to an end. If the model is being developed for, say, training, then the only purpose of the model is to facilitate training. And that's true regardless of what kind of model it is. These discrete event models that we've been talking about here are mostly for the purpose of analysis. What does that mean? That means that there's some question about a system, either a real system or some proposed system, that somebody wants an answer to. It might be something like how many servers should we hire? How many machines should we buy? Should we work on making our processing more efficient, faster? Is there something about the way that we are directing the various elements in our system that could be improved? Is there something about the communication that could be improved? All of these are questions that a simulation model, such as the ones that we have been developing here, could address. The question is, how can it answer these questions? Because up till now, I mean, the only purpose for your creating these models has been to address the torture that your instructor has imposed upon you. However, the purpose of these models is, again, to answer questions that somebody has about some kind of system. And that's what we're going to address now. Up until now, we have only been running our simulation once. And that is not a viable way to get an answer about what is going on with the system. And at least to start with, the canonical example you should think of is just with our basic queuing model. What is the average delay in the queue, or average number in the queue, or average number in the system, or maybe utilization? Any of those measures that we have been talking about and actually gathering in our models is subject to some question. What is the actual value of this? If you run a stochastic simulation once and try to glean some answers out of that, then that is not really a legitimate way to do business. So if that's not the case, then what is? Well, since you asked, I know nobody asked, but whether you asked or not, we're going to do it because that's my prerogative as the instructor. Okay, so this is our final topic, and it has to do with simulation output analysis. And we are only going to be able to dip our toes into this. This is actually a large field, and in fact, in the operations research department, they have an entire course devoted just to this. In other words, in that course, given that you have a simulation model then what kinds of things can you extract from that? What kind of information? We're trying to get the, when I say information, what are you trying to learn about the system? Again, think in terms of, let's say, delay in the queue. So for our simulation model, there is a no kidding actual value of a delay in the queue. So again, think of just our multiple server queue model. For a given inter-arrival time distribution and a given service time distribution, there is an actual, no kidding, expected delay in the queue, as we will have to define it very carefully in just a moment. But that's an actual number. The problem is we don't know what that number is. So to think of it even in more simple terms, supposing we have a coin and we want to know whether the coin is fair or not, or more precisely, we want to know what is the probability that if we flip this coin, what is the probability that it will come up heads? For a given coin, that's some number. You know, that's a no kidding number. There's nothing random about that. That probability is an actual no kidding number. The difficulty is that we don't know what that number is. Now, your intuition would be a good guide for this. If, you know, so let's say that for whatever reason you wanted to bet on these coin flips, and you want to make a good bet, and sort of to make the best bet possible, you would need to know what is the probability, say, that it comes up heads. And one minus that, of course, would be the probability it comes up tails. We assume that it's not going to land on edge. Okay, so now if you are allowed to examine this coin and do something with it for a while, that is not that affects it, but you're allowed to, you know, to look at it, examine it, and maybe flip it. What would you want to do? Again, intuitively, I am confident that each and every one of you would just sort of flip it a bunch of times and count the number of flips and count the number of heads. And your best estimate of what that probability of coming up heads, it would be the number of heads divided by the number of flips, right? I mean, that this shouldn't come as any astonishing revelation to anyone, but I mean, presumably that's what you would all do without having taken any courses in anything. You know, why? Because that makes the most sense. And that's essentially what we're doing here. Now, if you had that task and you had that coin, and what you did was you flipped it once and observed whether it came up heads or tails, how confident would you feel that you knew what the probability of heads was just by flipping it once? Intuitively, you wouldn't have much confidence at all. If you flip it once and it comes up heads, really the only thing you know is that it's not a two-tailed coin. Or if it comes up tails, you just know it's not a two-headed coin. So the point is, one flip does not give you much information about what that probability, that unknown probability, and we'll never know what that probability is. And intuitively, the more times you flip it and count the number of heads and the number of flips and come up with your estimate of the probability of heads, intuitively, the more flips you make, the more confident you are in that estimate, right? I mean, so in other words, the more times you can perform an independent replication of your experiment, the more confident you're going to be in the results. So again, if you only flip it once, you don't have a whole lot of confidence. Let's say you flip it twice. and you get one head and one tail, how confident are you that it's a fair coin, that the probability is a half? I mean, that would be your estimate, right? I mean, 2 flips, 1 head, probability is 1/2. How confident would you be in that? Hopefully not very. Performing our runs and what we're going to start calling replications of our simulations right now is just like that one flip. That one replication is going to be just like that one flip. And that gives us one observation on the thing that we're looking for. And so the natural thing, the intuitive thing is, okay, let's do that lots of times so that we have more confidence in what we have. Okay, so simulation output analysis, that's what we're talking about. The objective is to learn something about the system being modeled. See, there's the actual, what we really want to know is what is going on with our actual no-kidding system. So if we're the manager of this bank, say, and we're concerned about our customers' experience, and one dimension of that is the time that they have to spend waiting in the queue to get served, that's one dimension about that. So focusing on that, if we had a simulation model that would give us those observations, that would hopefully tell us something about the system being modeled. Okay, so here's the thing, is that we can't really perform experiments on our actual system because I mean, we could, but it would be challenging. So let's say that we wanted to perform at least 30 replications. Well, that would take us at least a month and a half if we're in a bank. In other words, we would have to observe our system for 30 days and collect stuff about it. And in a way, that might be the most reliable way to do that. But that's going to be expensive. It's going to be time consuming. And instead, we have this multiple server queue model, which captures many of the elements about our system. So if we can analyze our simulation model, then we might be able to make some inferences about our actual system. So our ultimate objective is to learn something about the system being modeled. That's our objective. And so what we have is, instead of the system itself, we have our simulation model of the system. So we're at least one step removed from that. The advantage is that we can just run the bejesus out of our simulated system, whereas we really can't do that in our actual system. Okay, now our discrete event simulations, they are typically stochastic. Every single one we've dealt with so far is stochastic. Now they don't have to be. You can create deterministic discrete event simulations. We haven't really dealt with those here. Why? Because they're not as challenging. If you have a deterministic simulation, then everything that we're talking about here is moot. One run is enough. If I have a deterministic model, then every time I run it, I'm going to get exactly the same answer. So there's no need for any statistics here. Okay, stochastic is just a fancy word for random. So just, and as you may have noticed, we academics like to use, we never use a large word when a diminutive one will do. Okay, so the point is, hopefully I've convinced you that one replication may not be representative of the system. And again, just keep this one in mind. Can you estimate the probability of heads from one coin flip? Okay, so output analysis. And again, our canonical models is going to be, we're going to go back to our simple multiple server queue. Everything that we do applies to every model that we've talked about. So what types of questions might we have? What is the average waiting time for customers? What's the average time to process a job? In other words, the time from not just the processing time, but the time from when the job enters to when it exits. That would be like the time in the system type of thing. Or in the case of our renege model, like what was the average percentage of lost customers due to reneging? That would be something that we would be interested in. When we created the reneging model, we ran it once and came up with a number. Again, how good was that number? How accurate was that number in terms of capturing the actual no-kidding percentage of lost customers? We don't know based on what we've done so far because we only ran it once. And again, running a stochastic model once and trying to deduce any conclusions from that are really viable is well, in the simulation world, a mortal sin. Okay, so we're going to focus on one measure. I've hopefully convinced you that a single replication is not sufficient. So we're going to do multiple independent replications. That's kind of where we're going to go. And again, hearkening back to your basic statistics class, if we want to estimate the mean, then we will typically do that with a sample average. That's a reasonable place to start. That's better than just running it once. Okay, so running it once and getting the mean, by estimating the mean by computing the sample average. Okay, so that's, when I say it's a good place to start, that means that but wait, there's more. What's the problem with that? The problem is that it still doesn't give us information about how accurate that estimate is. In other words, so I take my model, or again, let's think of our coin flip. So I flip it a number of times and I come up with an estimate of let's say 0.4. So I flip it 10 times, and 4 of the times I flipped it, it came up heads. Okay, so that's better than flipping it once. But how confident are you that that 0.4 is really close to what the true probability of heads is? With only 10 flips, I would be kind of not terribly confident. So that's where confidence intervals come in. And this is, you've all had, has anybody not seen confidence intervals in your stats class? Okay, so you all have, so you all know what a confidence interval is. Okay, so that's what we're going for. Why is a confidence interval useful? Because it gives information about how accurate that estimate is. Now, there's a little bit of a caveat about what a confidence interval means, and I'll probably fuss about it a little bit because your stats professor hopefully fussed about it too. But nevertheless, just having the estimating the mean by itself is typically not as useful as having a confidence interval about it. Why? Because if we have a very tight confidence interval, a very small confidence interval, then, I mean, confidence interval is so named because we have a certain degree of confidence, if you will, that the estimate that we came up with is indeed close to the one that we're trying to estimate, close to the true value. The thing to understand is we will never know what the true value is. We just won't. We have to accept that. But we can get close. And a confidence interval is a way of getting that close. So why are you not? There we go. Okay, so let's talk about some specifics here. So remember from your statistics class, okay, now where did that come from? We started with a random sample. And what does it mean to be a random sample? to have independent and identically distributed observations. So these are our observations from our system, and this is true whether we're measuring an actual system, or in our case, we're going to be looking at observations from a simulation. From our section on random variate generation, we noted that since underlying all of the random variates is a pseudo-random number generator, which is hopefully good enough, meaning that it produces independent and identically distributed uniform 0-1 random variables. We talked about how if I want random variates of a particular distribution, we learned a couple of ways to come up with that. We didn't learn every way, but we learned some ways. So if I want exponentials, then using those, I can come up with independent, identically distributed exponential random variables. And in fact, one way of evaluating your random number generator, your random variate generator, is to generate a bunch of these and compute confidence intervals for what you know to be the given mean. So for example, if I have an exponential random variate generator that I've implemented, and I want to know, okay, is this in fact doing a decent job? One way, not the only way, but I mean, at least one crude way of knowing, am I in the right ballpark, or is this kind of totally out of whack, is I generate a whole bunch of these, and then I compute a confidence interval for the known value. So let's say if I take an exponential distribution with a mean of 2.5, and I generate 1 million of these, and I estimate the mean and a confidence interval. If I have a really tight confidence interval around 2.5, then my exponential random variate generator is at least doing a reasonable job there. Now that doesn't, again, that isn't a substitute for doing goodness of fit tests and other types of things, but it's at least a first cut. If I'm off, and if it's off for the mean, then I know that something is wacky, and you need to fix it. Here, our x's now are going to be observations from our replications. So just peeking ahead a little bit, when we're going to look at a transient analysis, and so the average delay in Q that we come from one replication of our model is going to be one of these x's. That is one observation. So stepping back a little bit, so if we have a random sample of whatever kind, however we get it, our point estimator for this true but unknown mean, mu, is the simple sample average of them. And, and like to be fancy and have the sigma and all that sort of stuff, but this is something which should be review. And furthermore, an estimator for the unknown variance is this. This is the unbiased estimator because of the n-1. Does it need to be n or n-1? N-1 is kind of the standard, a standard way of doing it. There's actually an argument to be made for 1 over n, which is not, but that's something that one need not fuss over. Okay, so we have, the point is that in addition to estimating our mean, we have an estimate of the variance. And this is good only because our observations are a random sample, only because they're IID. If the x's are not independent, then this is a biased estimator. And that's something that we're going to have to deal with at some point. So, but given all this, given if we have a random sample, they're independent, identically distributed. So we have our estimate of the mean, we have an estimate of the variance. And so what is the confidence interval? And this is the approximate 100, 1 minus alpha. Remember, alpha is typically going to be either 0.05 or 0.01. Those are the two values. Why? I have no idea. That's just what statisticians use. So, so if anybody asks you, why was your alpha 0.05? It says, well, that's what, you know, that's kind of a standard one. Again, if you delve into your statistics notes, if they address that issue, then that's something like that. But this is not a class in statistics. We are using statistics to get the answers to the questions that we're asking, which are things like, what is the best estimate of the expected average delay in Q? Okay, we'll make that a little more concrete as in a short while. Okay, so what is our confidence interval? Well, first it's our estimate of the mean, and then plus or minus our student t quantile. And where does that come from? That comes from actually assuming that our observations are normal. And then it's n minus 1 because of, you probably heard some talk about it, degree of freedom. 1 minus alpha over 2, that's, you know, that's just kind of where we put the, see, a t is like a single hump distribution. It actually looks kind of like a normal. It's a little heavier tail than normal. But the idea is that we, the area in these is alpha over 2. And so this value right here, this is where that t value is. This is that t of n minus 1 degrees of freedom, 1 minus alpha over 2. So that's our sort of, in a way, it's kind of like a fudge factor. But then we multiply it by the square root of the variance, which is our standard deviation, divided by the square root of n. Okay, so this formula should be, if not on the tip of your tongue, existing in your statistics notes or your statistics textbook, wherever you have it. So hopefully you didn't burn your stats book at the end of that. Okay, so if we can come up with a random sample for the thing that we want, then we can use what we learned in statistics to form a confidence interval. And so that's where we can land, at least for the time being, because now we have an estimate of our parameter, estimate of this value. When I say an estimate of this quantity, such as the expected average delay in Q. And we have an estimate of roughly how accurate that is, given by our confidence interval. Okay, so that's the solution to this whole quandary on this. One replication is not enough. A few are typically not enough. In fact, we're going to use the magic number 30. Why? Because somewhere somebody said that if you have 30 replications, then the central limit theorem kicks in. Where did that 30 come from? I have no idea. But all I know is that if you say, well, the stats book said 30, then, it's the virtue of passing the buck. So just like if I choose a confidence level, an alpha level of 0.05 or 0.01, then those are two of the standard quantities. by choosing n of at least 30. That's again another standard quantity. However, particularly with simulations, with simulation models, more is better, more is good. But you want to have at least 30, if not for you know, because at 30 you can at least appeal to this unknown quantity that says at 30 observations, the central limit theorem. You've all heard this number 30 before, I hope. If not, then you know, we'll say 30, and trust me, if you look up in your stats notes somewhere, it's probably there. Okay, but now, when it comes to analyzing our simulations, we have two possibilities. Sometimes we don't have a choice, and sometimes we do, and that's why we have to sort of think about it a little bit. Those two choices are either terminating or non-terminating. Okay, just like there are two kinds of people in this world. There are those who think there are two kinds of people, and there's everybody else. Okay, so what's the difference? Well, in a terminating simulation, there is typically a natural, and I put natural in quotes, an end event or condition. Two canonical examples to just sort of think of is that if we have a little combat scenario, and we didn't have a chance to kind of to push our, when we were modeling movement and things like that. One thread of that is we could, when we added sensing and weapons and comms and other types of things, we could push that whole framework into a mini entity level combat, you know, situation or agenty type of scenario. We didn't have time to do that. In the follow-up class for this, which unfortunately nobody has time for, we actually do that. But if you know, just think of a combat, a simple entity combat type situation, there is typically a natural ending condition. That is, one side wins. You know, what does winning mean? I mean, that can be anything from attritting the enemy to a certain percent. It could be achieving, you know, reaching the objective within a certain time period. It could be inflicting X many casualties. Again, whatever, however winning is defined. In a typical combat scenario, it's terminating because it's not going to go on forever. An example a little closer to what the kinds of models we've been looking at, supposing I have a facility like a store or a bank, and it opens in the morning and it closes in the late afternoon, and that's how it operates. So that the opening and the closing are, the closing is a natural, quote, natural ending condition. So if it closes at 6 o'clock every day, notice that it opens at 9, closes at 6, then that's how it operates. And these are going to be this terminating one is going to be what we deal with first. Non-terminating, there is no natural end conditioning. In other words, we can run it indefinitely. So for the same multiple server queue model, say, we can just kind of keep running that for forever. In fact, as we've done for our single runs, like we've run it for 100,000 time units, and that, you know, that may not necessarily be the way the actual system runs, but that is a way to determine our steady state values. And it turns out that way of analyzing things is a little bit trickier than the terminating one. So we're going to deal with the terminating ones. But when I say non-terminating, there are typically only two choices of two outcomes of how the system works. It will either reach some steady state, which means that no matter how far you run it, it will keep fluctuating around the same values. It may fluctuate wildly, but it will still fluctuate. Or it will blow up, meaning, well, in the case of a queuing system, either the queue size will sort of fluctuate and periodically empty out, or the queue will just kind of blow up, meaning it grows and grows and grows. And if we kind of put in parameters in our model such that this happens, then you kind of see that, because typically these queuing models blow up pretty quickly. So now if our actual system does not do that, then, and we're looking at steady state, then then what that means is that our parameters need to be such that this steady state is reached. These are pretty much the two main possibilities. There's one called, there's a third option called periodic steady state, where it actually follows some kind of seasonal pattern. Again, for certain situations, that's actually a reasonable way to look at that. That's a bit of complexity that we're not going to consider here. So that is a possibility. There are other possibilities, but these are two of the main ones, and that's what we're going to be looking at here. So we're going to start with a terminating simulation. And the immediate problem with our terminating simulation has to do with what is it that's being estimated. Okay. Now again, let's think back to our canonical example, which is a multiple server queue, and we're looking at the delays in the queue for each successive customer. Now I claim that those individual delays are not, and this is important, they're not independent and identically distributed. Okay, so let's look at let's think of a thought experiment for this. They're not independent one from the other. Okay, why? Well, let's pick out a customer who happens to have a larger than average delay in the queue. Whereas our system is going along, each of our customers are getting their delay. There is some kind of average that's kind of going along. And if that, well, actually, there's a simpler way. Supposing, let's look at k equal 1. We have one server. So what's the very first delay in the queue for the first guy? The first delay in queue is going to be 0. What about the second guy? Well, the second guy is going to be, it could be, the second guy could be 0, but only if it comes in, that customer comes in after the first guy has completed service. But the second customer might come in while the other one is in service. And so the expected delay of the second guy is going to be bigger than 0 in general, but only by a little bit. But then what about the third guy? So the third guy, well, he could be 0 too if he comes in after the second guy is finished. But remember, the second guy is kind of waiting for the first guy. And so in general, that third guy is also going to be bigger than 0, but in their expected delay in queue is going to be bigger than the second guy. And they're all going to be bigger than the first guy because he's always 0. So basically, they're not identically distributed. And they're not even independent. Okay, so what that means is, see, it would be nice if these guys were independent and we were interested in the delay in queue, then we could just sort of take our estimate and from that one replication. The problem is we can't. And furthermore, the tricky part is, what does it mean to take the average of things that are not IAD? So at the end of this run, we're going to have a single, remember we were, for our entity server, we had the average delay in queue over that replication. But what did that mean? That was simply the average delay over the day of our customers. I mean, other values we might be interested in might be the maximum number in the queue over the day, or the average number in queue over the day. And there, well, if we look at the average number in queue over the day, remember that the number in the queue is, it typically will look something like this. So that's a time varying guy, and for the time varying things, there's really no independence. Okay, so here's the difficulty applying the quote normal statistics to the raw simulation data. That is, these delays in queue, these raw delays in queue. Since they're not typically independent identically distributive, see, each of these guys actually has a different mean. And they're not independent either. Because if, again, let's just sort of think about what's happening here. So if I know the value of a particular customer's delay in queue, and let's say it's fairly large compared to some of the others, what about the next guy? Does that give information about the next guy? If I say that the 10th customer waited a long time in the queue, what about the 11th customer? Well, where did the 11th customer come from? He came in after this guy. And if this guy was waiting in the queue a long time, the chances are that the guy after him was also waiting in the queue a long time, because he was right behind him. Or let's say the 20th guy had a really low delay in queue. Let's say the 20th guy, maybe he had 0 because when he showed up, there was an available server. Well, what about the next guy? What about the 21st guy? He probably had a much lower one. So if I know that one customer, if I know what their delay in the queue is, then I have information. I don't have perfect information, but I have information about that next one. And what that means is that they're not independent. Again, typical coin flips are independent, because if I flip a coin, say I flip a coin 5 times, a fair coin, I flip it 5 times, I get 5 heads in a row. What's the probability I get a head on the next one? It's still 0.5 because they're independent. But here, if I have a large delay, then the chances are the next guy is also going to be large. Okay. So having said all that, how can we do business? And again, just thinking of our canonical delay and queue. Okay, so our usual mean, and this is what we've been computing with our simple stats tally. This mean is one observation of the expected average delay in queue for the first, say, n customers, or over the day, as we will see. Okay, so that's one replication of the simulation gives us one observation of the expected average delay in the queue for the first n customers. Okay, notice the 2 modifiers, expected average delay. Why? Because what we're measuring is the average delay, and the parameter we're trying to estimate is the expected value of that. So to form a confidence interval, we're going to perform, now n, I make this capital N just to distinguish it from the lower n. We're going to perform n independent replications of our simulation, and we're going to get n of these means. And so how now, because these are independent replications, and each of these is being done under the same initial conditions, the same circumstances, we now have IID. These are now IID. And so now we can apply our regular statistics to these values. So I take the mean of the means, and traditionally we give that a double bar, and then the estimate of the variance likewise is the estimate of the variance of these observations. And so our mean of the means, oops, there should be a second bar here, plus or minus, again, our standard deviation of the means. Then this is our number. There should be a square root here. T n minus 1, 1 on itself for 2, etc. And that's the formula. Oops, that's where we are. Okay. Okay, so you're probably thinking, okay, all of that is fine and good, but how do we do that? Well, after a short break, I will show you.